Chandler Science, AP Physics 1, graphing. This video will be all about graphs, mainly position versus time graphs and velocity versus time graphs. We'll touch on acceleration versus time graphs a little bit. I had made one real long video initially that was all about kinematics and graphing kind of together, but it got really long and I don't want to make you watch a 30-minute long video, so I cut it up into two. Don't forget, if you're one of my students, to have 3 questions along with your notes ready for class next time I see you. And if you're from anywhere else on the internet, welcome, and I hope you enjoy. So without further ado, let's dive right into a position versus time graph. Alright, so first we'll take a look at a position x versus time t graph. So you'll see here we have a straight line going down like that from our initial position here to our final position here. And we already derived in class the equation x equals v delta t plus x naught. And if you were confused by that derivation, remember we just used the equation of a line, y equals mx plus b. And since we know that the slope is velocity, we know that because the slope of a thing is m equals y2 minus y1 over x2 minus x1. That's a 2. And what's happening on the y-axis is change in position. And just like our velocity said, the definition of velocity is change in position over change in time. So since the y-axis is our position that's changing and the x-axis is our time that's changing, it turns out that our slope is simply the change in position over change in time. So we can substitute in, for n we substitute in a v. For the y we plug in an x, since on the y-axis is position. On the x-axis is time, we plug in a t for time. And on the y-intercept, we have where we started, right? Our initial position there, so we plug in x naught, and that's how we got our equation. So I just want to recap real quickly this graph. We have the slope equals velocity on a position time graph. And in this particular example, because it's a straight line, we have constant velocity, right? Because it's not changing. The slope of this line is the same down here as it is here, as it is here, everywhere. It's the same slope at every position, so it has a constant velocity. All right, so let's look at a more complicated graph now. All right, so here's a little more complicated graph. Again, we're going to look at a position x versus time t graph. When we have a graph like this, it's kind of curvy, right? It's not just straight lines. We got to be a little more careful in our thinking about what's happening to this object. And very often in class and on tests and exams, we'll be asked to given a graph and then to describe the motion of the graph, right? Or vice versa, we'll describe the motion to you, then you'll have to draw the graph. But either way, you got to understand how these things work. You'll notice this part of the line here. Oh my gosh, that was a terrible line. Let me redraw that. This portion of the line here is pretty much straight, right? Not really changing too much. So in this portion of the graph, our velocity is constant. It's not really changing, right? So we're going at a steady pace. So maybe here's a runner, and he's running at a constant velocity forward to the right. We know he's going to the right, or in the positive direction, because the slope here is positive, right? It's going up, for lack of a better word. But what happens in this region right here? You can see how it kind of starts to flatten out, gets flatter. Now, if it's getting flatter, the person is still running to the right, but they're not going quite as fast anymore, right? They're starting to slow down. And again, we know that because the slope of the line is getting flatter, right? It's getting less steep. If you ever wonder about this, you can take the tangent line at different points along the way. So for example, if I take a point right there, draw the tangent line, and that's a line that intersects the graph at only one position, and I do it again, say right here, you can see how this line is much flatter than that other line, which is because I'm slowing down. The slope of the line, tangent line, is getting smaller. And then there's a very special point right at the peak of that graph. I'm going to erase this real quick. Right at the peak, right here. So if we draw a tangent line at that point right there, we get a flat line. Now that means that at that particular moment, just right at the peak of the graph, my slope of this line is 0. Well, if slope is velocity, that means I've actually stopped for a moment. For one instant, I've stopped. So at that point, the runner, he stops, right? He's tired, needs a breather, stops for a second, catches his breath. But then immediately after the stop, look what happens to our slope. Now it's going down, and it starts off kind of flat, but then it gets steeper and steeper, right? So what happens now? The runner actually turns around, starting off slow, but now he's going faster and faster into the negative direction. We know it's negative now because the slope's going down, and if you were to find the slope of the tangent lines on this part of the graph, you would find that the slope is actually negative. because he's going in the negative direction. So he turns back around, runs back to the origin, but then again, right around in this region of the graph, what's happening is the slope again starts to flatten out. You can see the tangent line is getting flatter and flatter and flatter. So he's still going in the negative direction, but now he's getting slower, slowing down. Eventually he's going to, right around in this region, see it's basically a flat line. He stops again. The runner is done running and he's kaput, right? And you'll notice that our initial position is here. Is actually, so my drawing, this drawing here is not very accurate, right? Because my final position, let me erase some of this real quick. My final position is right about here, right? That corresponds with my position here. You kind of trace it back this way. And my initial position was here, which means that I should be a little bit to the positive of where I started, right? So I didn't draw this very accurate, but you get the idea. So really I started like here, is where I started, and then I would have ended like here, just a little bit to the positive, in the positive direction of where I started. You see that? All right, so that's position time graphs. Now we're going to move on to velocity time graphs. All right, so now let's take a look at a velocity time graph. So we got v on the y-axis, our velocity, and time t on the x-axis. Now you'll see here we just have a simple, pretty horizontal line, right? What this tells us is that we have a constant velocity. A lot of times students get confused and they think, and they see this flat line, they think, oh, the object is not moving. It's true on a position time graph if you see a graph like this, but not on a velocity time graph. So the first thing you always want to look at when you are examining a graph and kind of deciphering it and doing a problem with a graph is the first thing you look at is what are the axes? Is this a position time graph, velocity time, work times displacement, and what kind of graph we're dealing with here, right? So velocity time, let's say this velocity is, I don't know, positive 3 meters per second. So that just means that as time ticks by, our velocity is always 3. So we have no acceleration. Turns out the slope of a velocity time graph is acceleration. And we know that because, again, the slope formula is change in y over change in x. And on our y-axis, we have change in velocity. And on our x-axis, we have change in time. And that is literally the formula. Oops, not an x, sorry. Change in time. That is literally the formula for acceleration, right? So the slope on a velocity time graph is acceleration. Remember that? Don't ever forget. All right. So pretty simple. Now I want to also draw, kind of translate the graph from a position time graph, from a velocity time graph to a position time graph. And that is the worst ever. Okay, let me try to draw a straighter line here. I can do it. There we go. All right, not bad. All right, so what would this look like? This information on this side, if you want to kind of translate it over to look like a position time graph. Well, hopefully you realize that since the slope on a position time graph is velocity, and our velocity is constant at positive 3, that we're going to start at the origin. Since we don't really know where we start, the velocity time graph does not tell us where we start. It only tells us how fast we're going. So we're going to start the origin, it's a good place to start, and have a positive 3 slope, positive 3 velocity the entire time. It's a straight line. So you see this one goes at an angle, and the velocity time graph is flat. General rule of thumb, if you ever draw your position time graph and your velocity time graph and they look identical, you probably messed up. So go back and look at it because they very rarely ever will look identical. All right. The other thing we want to talk about when it comes to velocity time graphs is we need to know. I'll write this somewhere else. That we need to know that the area under the curve. Let me rewrite my acceleration formula real quick just in case. All right. The area under the curve. So for this guy here. This area in here is equal to the displacement, delta x. That's super important to remember, right? Now I always say area under the curve in bunny quotes because it's not really under the curve. We'll see an example in the next problem on the distinction here. But a better way of saying it is perhaps the area between the graph and the x-axis, all right? So you shade that area in, and it's always going to be rectangles or triangles, so you can usually find the area pretty easily. If the graph ever stops like this, like it's kind of hanging off the edge and it doesn't doesn't go all the way to the end of the graph, just draw a line straight down or up vertically to the axis and make that the side of your rectangle, right? So we have, let's say this was 10 seconds, right? So we have positive 3 is the kind of the width of my rectangle, and 0 to 10 is the length of my rectangle. So this would be 30. Would be the area, and that will also be my displacement. All right. So let's try another one here. This time we have a velocity time graph, and first thing I want to do is find the slopes. Right. So this slope here would be my acceleration. this slope is acceleration. There's no acceleration here. It's a here is 0. Let's just say this is a is I don't know, how about negative 3, and let's say a on this side is positive 4. All right. Just makes up some numbers here. Okay. All right. Now first thing I want to do is kind of translate the graph from my velocity time graph to a position time graph. And again, feel free to kind of practice on your own, and then check yourself pause the video and do it, and then check yourself against me in a minute here. Now, it gets a little more complicated now when the velocities are changing, okay? And kind of going up and then down and all that sort of stuff. So we got to remember here that the acceleration is a positive 4 here. Our velocity is changing. That means we're going to have a curved line on the position time graph. It's not going to be a straight line like before. It's going to be curved. Now, first thing we ask ourselves is, all right, where are we starting, right? Our velocity starts off in the negative region, right? These are negative numbers down here. It's negative 3, say, maybe positive 4 up here. So if we're starting in the negative region, that means that our slope here should be negative, right, going down, because our velocity starts off as negative. Now we got to ask ourselves, okay, are we speeding up, getting faster and faster, or are we actually slowing down? Now in this case, from here to here, we are slowing down, right? Look at the numbers, negative 3 to negative 2 to negative 1 to 0. See how it's getting negative 2, negative 1 to 0. So we're actually slowing down. That means that our slope of this line should be getting flatter, right? Now right here, at this very special point, right there, it's a very special point, because look at our velocity. Our velocity at that moment is 0. And that tells us that we have no velocity. If we have no velocity, we have no slope on our position time graph, right? So we should have a perfectly flatten out right there. Now look what happens to our velocity in this region. Let me erase this stuff so I'm not so busy in here. What happens to our velocity in this region? Look. Now, it starts off real low, right? But then it gets positive and it gets bigger. Right? So now it's positive, so I'm going to be turned around. Now we have a positive slope on the position time graph. So now we're going to swing back the other way. Starts off kind of flat, right? Because look, down here, we have very small velocity, but then it gets bigger, so we get steeper and steeper. It starts off kind of slow, and then it gets really steep here. And then what happens right in here? Look, we have no acceleration, but we do have velocity. A lot of students think, oh, we come to a rest right there. No, we don't come to a rest. We just stop gaining velocity. So what happens is we flatten out. Have a straight, I shouldn't say flatten out. We have a straight diagonal line, right? Not flat like this, not horizontal. That would be stationary. But we have a constant slope, right? And our slope should correspond to velocity. So we should have about a positive 4 slope on this line, right? So it kind of curves down, comes back up like a parabola, and then comes up here and then kind of straightens out like you see right here, right? Constant slope. Now, again, what happens in this region? Okay, down right here, in this part of the graph, again, we still have positive velocity. And a lot of students want to make the mistake of thinking that we turn around. We are not turning around, okay? We have not changed direction. We're just slowing down, but we're still going in the positive direction. It's like you sprint really fast, you're running as hard as you can in one direction, and then the race is over, so you kind of slow down, right? You kind of stop running as fast, but you're still going in the same direction, right? You're just slowing down. So look at our velocity. Start at positive 4, and then right here, we're at positive 3, and maybe then here, we're at positive 2, and then positive 1, and you get the idea, and then we're at 0, okay? So what's going to happen is we're going to flatten out, right? And then at the end, there we should have a nice flat. Now at this point right here, we should be flat, right? Because since we have no velocity, and then so no slope on the position time graph, okay? That's a lot to take in, so feel free to rewind and watch it a lot in practice, and you guys can even make your own velocity time graphs and then draw the position time graph and then bring it to class and ask me if it's correct or whatever, right? So practice makes perfect with this stuff. The more you do it, the better you'll get at it. So I encourage you a lot to try some of your own. Just make up a graph, right? Just draw some lines and then see if you can translate it to the correct graph, right? Now with that said, let's go ahead and erase all this stuff here, and I want to talk about area under the curve real quick, okay? So I'm going to erase all this stuff. Erase most of it anyway. Okay, and now let's look at area under the curve. Now, we said the area under the curve is displacement. So here we have, on this part of the graph here, since it's actually below the x-axis, remember we're going to shade in the part of in between the graph and the x-axis. So this part of the graph, I would shade in, right? See how I made a little triangle here? Below the x-axis, that's what the graph is. Now the rest of this graph I'm going to cut it into pieces. I'll make a triangle out of that piece, a rectangle out of this piece, shade that in, and a triangle here, right? Now I don't have numbers on this graph, so I can't actually do the math right now. I'm not going to spend time doing that. But the displacement on this part here would actually be negative, right? Because it's below the x-axis. I have negative velocity. So let's say that this is pretend. I'll make up some numbers just for fun. Maybe this is -5, this area under this curve, and then this triangle here was 10. This triangle here was 30, and this triangle here was say it was 20. So to find the total displacement of the whole graph, we just add up all the numbers that correspond to each section of the area we've discovered, right? So we have 30 plus 20 is 50, plus 10 is 60, minus the 5, so we get 55. Which, if you think about it, makes sense, right? We started running in the negative direction, but then we turned around and ran a whole bunch in the positive direction. So it looks like we should have a positive displacement, and we do. Our positive displacement in this example will be positive 55 meters, right? But you never know, sometimes you get displacement in the negative, and that's totally fine, but in this example, positive 55 meters, all right? So hope that makes sense. We're going to do a little bit more with graph translation, and we'll do that in the next couple slides, all right? All right, we're actually going to talk about acceleration time graphs real fast. I forgot about that, but I'm going to throw it in here. You don't see acceleration time graphs too often on the AP material, but it has cropped up occasionally, so I want to talk about it. You're only ever going to see horizontal lines or vertical lines on acceleration time graphs in this class, all right? So let's say this is +1 and -1 here. All right, all you got to remember here is that the area under the curve, right, under the curve, and again, between the curve and the x-axis, so maybe negative region down here, the area A under the curve equals, on an acceleration time graph, the change in velocity, right? It's just useful to remember this because you're going to get one of these eventually, and a lot of students get like bewildered, like, oh my god, what do I do? All I know is acceleration. Well, now you also know change in velocity, all right? So if we're going to draw a velocity time graph based off of this acceleration time graph, it's pretty simple. We know that from the start to all this region in here, we have a +1 velocity. Now remember, the slope of a velocity time graph is acceleration. So acceleration is 1, that means our slope should be 1. And then bam, look, it changes instantly from right here. It changes instantly down here to -1. So what happens? Well, now our slope becomes -1, and we should get a graph that looks something like that. Right? We could even go ahead and draw the position time graph based on this. I'll kind of do it in here. So again, we have a kind of increasing velocity. So we start off, it is positive. So we start off here going up, getting a little bit faster, but then we start to slow down, back to 0. So we kind of flatten out like that. So it kind of looks like almost like a sideways S, so to speak. All right, so really important to understand that acceleration area under the curve is change in velocity, and to be able to kind of translate these graphs to different types. All right, we're going to spend a little bit of practice on that on the next slide. All right, so let's do 2 practice translations here. Now, we already did a lot of velocity time graphs and then translating that into position time graphs. So I want to go the other way now. I want to go from position time graphs like this and translate those into a velocity time graph. So I'm just going to kind of make a graph up here. I'll go like there and down and then kind of flatten like that. All right, so let's do a velocity time graph. And again, feel free to pause the video and kind of draw it out yourself to see if you can get it correct. All right. So what's happening here? Well, let's see. This is pretty flat. I'm going to draw this flat like this. Okay. Pretty much flat in here now. But if the position time graph, the slope is velocity, right? So that means that this graph is flat. The slope is 0. So we don't really have much velocity in here. I'm going to change color just so it makes it different here. Nice pink color. So pretty much no velocity in the beginning here. This first little section, right? Now this next section, what's happening now? Our slope. Remember the little help ourselves with the tangent line. Ooh, look, it's getting steeper in the negative direction. That means I'm going to speed up in the negative direction, right, this way. And then right around in here, looks like this line is almost a straight line, right? It's not really curving anymore. It kind of straightens out, which means I should have constant velocity. So a pretty flat line in there. Now, but in here, this region here starts to curve again, flattening out, right? Remember, getting on the position time graph, slope is velocity. So if the slope gets flat or closer to 0, that means I'm slowing down. So I'm going to slow down here. And notice the slope is still negative though, right? It's negative slope. So I'm still negative velocity, but I'm getting slower towards 0. And then right in this region here, I basically stop, right? So I've come back to the 0 portion, and then I'm back at 0 velocity, right? So if you drew this graph, your velocity time graph should look something like this, kind of like this stretched out U, okay? All right, let's do one more where we practice doing from position time to velocity time. This time I'll start down here. Let's go up real steep, and then we'll go back down like this. All right, so I'm going to do this position time graph. Now let's do the velocity time graph of this guy. Let's change colors again because I like to change colors. That pink is nice. Let's do that. All right, here we go. All right, now look. What is a couple questions to ask yourself when you start, right? What's my slope, and am I speeding up or slowing down? Well, again, this region looks fairly, I did it by freehand, so it's more or less a straight line, right? But it's really steep in the positive direction. So I must have a lot of velocity right out the beginning, right? A lot of positive velocity. Again, a lot of students want to think, oh, on the position time graph, I'm below the x-axis. That's negative. Yeah, your position is negative, but doesn't tell you anything about the velocity. Our velocity is positive because the slope is positive. So that means I'm going to start up here in the positive region of the graph because my slope is positive initially. Now, pretty much constant here, really up high for this first part of the graph, but then what happens in this region, look, it starts to curve and flatten out, right? So I'm going to slow down. Slope is still positive though, right? Still have a positive slope, so I'm still above the I'm in the positive region here on my velocity time graph, but I'm slowing down. I'm approaching the 0 mark. I'm getting down here, right? And right about here, in this region, right, in this spot. Whoa! Let me do that. In this spot right here, I have 0 slope, right? Which means that's the spot where I should be crossing the x-axis on my velocity time graph, because that's where I have 0 velocity, right? And look what happens. We start to speed up in the negative direction. Now that our slope is negative, we turned around, right? So whenever the velocity time graph crosses the x-axis, that's the key to telling you you have turned around, right? Now we're in the negative velocity region. Now we're down here, and then notice in this part right here, it's pretty much straight, so I'm going to kind of draw a flat line. And then right in this region here, it starts to flatten out again, and goes back to 0, and then we're at 0 velocity. Okay, so something like that. This is all kind of just free-handed, qualitative, not quantitative. We're just kind of getting the shape down, but hopefully you got a shape kind of looks something like that. Okay, if not, feel free to shoot me an email in class, or message me on Remind, or ask me after school. All right, so that's it for this video. We've talked about all kinds of graphs, how to translate them, what they mean, things to calculate from them. We did some sample problems. Hope you guys had learned something. Forget, if you have any questions, don't hesitate to ask me in class or out of school or outside of class. Don't forget 3 questions at minimum. Turn those in next time I see you in class. And hope you enjoyed. Thank you guys. Bye bye.